Retrocausality in quantum mechanics is a fascinating concept where future events can influence past ones, challenging our usual understanding of cause and effect. Imagine you have a movie of a ball rolling down a hill, and you can play it both forward and backward. In our everyday world, the ball starts at the top and rolls down due to gravity. However, in the quantum realm, it's like the ball's behavior can be affected by events that haven't happened yet, as if it knows the future. For example, in the famous double slit experiment, particles such as electrons behave differently depending on whether their path is observed. Even more intriguingly, if the decision to observe or not observe is made after the particle has passed through the slits, it still seems to know and behave accordingly, as if future measurements are influencing past events. Another example is the delayed choice experiment, proposed by physicist John Wheeler, where choices made about measurements after particles have traveled some distance can seem to retroactively determine their earlier behavior. Retrocausality is important because it challenges our fundamental understanding of time and causality, which are pillars of classical physics. If future events can influence the past, it could lead to new ways of thinking about time travel, information processing, and even our understanding of free will and determinism. In practical terms, it might also impact technologies like quantum computing and cryptography, where the manipulation of information at a quantum level could exploit these strange temporal effects. Understanding and harnessing retrocausality could potentially revolutionize how we approach problems in physics, computing, and beyond. To grasp retrocausality, we must venture into quantum mechanics. This branch of physics reveals a reality far stranger than our everyday experiences. Particles don't behave like predictable billiard balls. They exist as both particles and waves, governed by probabilities. The double slit experiment shows particles interfering with themselves. This uncertainty is known as superposition. Imagine a spinning coin, neither heads nor tails until caught. Observation influences the observed, hinting at retrocausality. Could future observations affect past behavior? Prepare to challenge your notions of time and causality. To truly grasp retrocausality, we must journey into the quantum realm, a microscopic world governed by rules that defy our everyday intuitions. Here, particles exhibit behaviors that seem paradoxical and almost magical. One fundamental tenet is wave-particle duality. Imagine a photon behaving as both a particle and a wave. This dual nature influences how particles interact. Think of an electron existing as a cloud of probability. Its location is smeared out like a blurry photograph. This uncertainty is a fundamental aspect of the quantum world. Imagine a spinning coin, neither heads nor tails until observed. In the quantum world, particles exist in a superposition of states. The act of measurement collapses possibilities, central to quantum mysteries. Experiments challenge our notions of cause and effect, suggesting the future might influence the past. The double slit experiment vividly illustrates the perplexing nature of the quantum world. Imagine shining a beam of light at a barrier with two narrow slits. Instead of two bright bands, an interference pattern appears. Light waves interfere like ripples on a pond. The surprise comes with individual electrons. They also create an interference pattern. Highlighting superposition, electrons pass through both slits at once. Observation collapses the wave function, raising profound questions about reality. Uncertainty reigns, superposition, and the observer. The double slit experiment unveils a fundamental principle of the quantum world, superposition. Quantum particles exist in a haze of probabilities, occupying multiple states until a measurement forces them to choose. Particles like electrons and photons exist in a superposition of states until observed. Observation disrupts superposition, collapsing the wave function into a definite state. In the quantum world, observation participates in reality's unfolding. The arrow of time, causality in classical physics. In classical physics, time's arrow flies straight, always pointing from cause to effect. In the macroscopic realm, causality reigns supreme. Imagine a line of dominoes, each poised to topple its neighbor. When the first domino falls, it sets off a predictable chain reaction. This is the essence of causality. Every effect has a cause. In the classical world, this cause and effect relationship is absolute. Newton's laws describe how forces act upon objects with precision. Apply a force, and an object accelerates, a clear cause and effect. This understanding shapes our perception of time itself. We see time flowing forward, driven by cause and effect. The past is fixed, the present unfolds, and the future is shaped by our actions. To solidify our understanding of causality in the classical realm, let's consider a few concrete examples. Picture a game of billiards where the cue ball, propelled by the player's strike, collides with another ball, sending it careening across the felt. The cause, the cue ball's impact, leads directly to the effect, the second ball's motion. Similarly, imagine a ripe apple detaching from a branch, succumbing to the relentless pull of gravity. The cause, the force of gravity acting upon the apple, results in the effect, the apple's downward acceleration and eventual thud as it hits the ground. These examples, though simple, illustrate the fundamental principle that underpins our understanding of the physical world. Every event has a cause, and that cause precedes its effect. This principle, deeply ingrained in our intuition, forms the bedrock of classical physics and shapes our perception of time as a one-way street, always flowing from past to future. This seemingly unshakable foundation of causality, however, begins to crack and crumble as we delve into the enigmatic world of quantum mechanics. Here, in the realm of the very small, where particles behave like waves and uncertainty reigns supreme, the clear lines between cause and effect blur, challenging our classical intuitions and opening the door to mind-bending possibilities like retrocausality. The subatomic realm, governed by quantum mechanics, defies our classical intuitions. Particles can exist in multiple states simultaneously, their properties undefined until measured. Does observation shape the outcome? Imagine quantum billiards, where paths are undefined until impact. Can we claim the cue ball's trajectory caused the movements? These questions challenge our understanding of the universe. Imagine a world where a message sent today mysteriously alters a letter written yesterday, or a choice made now ripples backward in time, influencing a past decision. This is retrocausality, the idea that the future can influence the past, that effects might precede their causes. It arises from certain interpretations of quantum mechanics, where the act of measurement shapes reality. Could this influence extend beyond the present moment, reaching backward in time like echoes from the future? In Wheeler's delayed choice experiment, the decision to observe a photon can retroactively determine its past behavior. This mind-bending concept suggests that our present choices can influence the past, challenging our conventional understanding of time and causality. The transactional interpretation visualizes how the future might influence the past in the quantum realm. A quantum event involves a negotiation across time, with an emitter sending an offer wave forward and an absorber sending a confirmation wave backward. When these waves intersect, they establish a transaction that determines the photon's path. This handshake ensures a consistent narrative, intertwining the past and future in a delicate dance of possibilities. When particles defy distance and time, they exhibit behaviors that challenge our understanding of the universe. Quantum entanglement shows us that particles can be interconnected in such a way that the state of one instantly influences the state of another, regardless of the distance between them. This phenomenon, often referred to as spooky action at a distance, has been confirmed through various experiments. Additionally, delayed measurement experiments suggest that our actions in the present can influence the past states of these particles, hinting at the mind-bending concept of retrocausality. Retrocausality presents a paradox, challenging our understanding of cause and effect. How can an effect precede its cause without violating the laws of physics? Some argue retrocausality operates within strict boundaries, preventing paradoxes. Others suggest a self-consistency mechanism ensures a consistent timeline. Reconciling retrocausality with reality might require uncovering hidden mechanisms that prevent paradoxes, pushing the boundaries of our knowledge. Retrocausality challenges the notion of free will, suggesting our choices might be predetermined by future events. Imagine a chess game where each move is predetermined by the opening. This deterministic view suggests our actions are shaped by both past and future events. If our future is already written, what does it mean to strive, hope, and dream? In a deterministic universe, Free will is an illusion. Our choice is predetermined by prior events. Retrocausality supports this view, suggesting future choices shape past events. Our sense of agency might be a side effect of the universe's unfolding. If our fates are sealed, what is the point of seeking meaning and purpose? From theory to the technological frontier, quantum mechanics and retrocausality are paving the way for groundbreaking advancements. Quantum computers, with their glowing qubits and intricate circuits, are at the forefront of this revolution. The exploration of quantum mechanics concepts has led to real-world applications in quantum computing. Imagine a quantum computer uncomputing a calculation, showcasing the potential of retrocausality. Developing retrocausal algorithms for quantum computations is a challenging yet promising endeavor. These algorithms can revolutionize fields like cryptography and more. By harnessing the laws of quantum mechanics, we can achieve unprecedented technological advancements. However, the practical implementation of retrocausal technologies comes with its own set of challenges. Precision manipulation of quantum systems is crucial to achieve the desired retrocausal effects. Retrocausality resides within a larger tapestry of interpretations of quantum mechanics. Each interpretation offers a different lens to view the quantum world. The Copenhagen interpretation posits that measurement collapses a quantum system's wave function. The many-worlds interpretation spawns new universes with each quantum measurement. The transactional interpretation suggests a handshake across time between emitters and absorbers. Navigating this labyrinth of interpretations is an ongoing challenge for physicists and philosophers. Our journey through retrocausality takes us from cause and effect to the quantum realm where time blurs. We've explored Wheeler's delayed choice, entanglement, and philosophical conundrums. Does retrocausality represent a genuine paradigm shift or a theoretical curiosity? The answer remains elusive, fueling debate and research. The implications challenge our notions of time, causality, and reality. If fundamental, it suggests a universe where the past and future are entangled. As we explore the mysteries of quantum mechanics, the future of reality itself seems to be reshaped. The integration of retrocausality into quantum theory opens up new avenues of thought, challenging our conventional understanding of time and causality. Scientists are on the brink of discoveries that could redefine our perception of the universe. The quest for a unified theory of quantum gravity continues, with researchers exploring the quantum realm with unyielding curiosity and wonder. The journey is far from over, and the masterpiece of quantum mechanics remains unfinished.